Hello. So far we have talked about calculus of variations and its role in mechanics, and we have also been emphasizing the fact that calculus of variations has a big role to play even in optimal structural design. We have considered this problem in the last couple of lectures and developed enough theory for it. Today we will actually solve the problem, and the problem that we are considering is a bar. Okay. So, it is a normally you take a bar to be of uniform cross section, but since we are designing a bar today, let us take the axis and show that the bar can have an arbitrary area of cross section. This is the problem that we have been taking as a motivating example for including constraints in calculus of variation. So, everywhere if I take the cross section, that is A of x, where x is this, x equal to 0 at that point, and at this point x equal to L, because the length of the bar is L. Okay. And what we are trying to do is to make this bar as stiff as possible, meaning we want to minimize the strain energy of the bar, which is given as a functional 0 to L half E A u prime square dx. Let us recall that u of x is the axial displacement when there is a force applied on the bar. Axial displacement, and of course E is the Young's modulus of the material, that is the stress strain relationship, and A of x is the area of cross section. So, that is the area of cross section, which is our design variable. So, we minimize with respect to A of x the strain energy, and we have constraints here because this u of x in this problem is what we call state variable. State variable, it indicates the state of deformation of the bar here. That has to be governed by a differential equation which we had derived earlier, which I will write A u prime prime plus p equal to 0, where p of x is the axial loading. Axial loading. So, it is going to at every point there will be some loading, more less depends on what p of x function that we give, that is axial loading, that is p of x. And the moment we have a function type equation, then we have to put a corresponding lambda x, which is the Lagrange multiplier. Okay. This is the governing equation, differential equation, which is the function type constraint. So, corresponding multiplier is also a function. And then we have the volume constraint. We have been writing this problem in the last 3 lectures. This is the resource constraint or volume constraint, which is a functional type constraint. Hence, the corresponding multiplier is just an unknown constant which we denote as uppercase lambda. Okay. So, this is our problem. So, this is our problem, that is we want to minimize the strain energy so that the structure, that is the bar, will be as stiff as it can be. We are minimizing strain energy means that we are not letting it deform a lot, that means that it is very stiff under the given loading. We should not forget actually to write the data for the problem. Data. So, we are given the length of the bar, we are given the Young's modulus of the material of the bar, we are given the loading p of x, and we have specified an upper bound on the volume of material. So, V star here is volume of material. Okay. So, this actually completes our problem, otherwise we do not know what is given and what is to be found. Okay. We are given the length of the bar, Young's modulus, load P of x and V star. Now, we need to find, what should we find? We have to find obviously A of x, because that is our optimization variable. In the process, we have to deal with our state variable also, U of x, that is also unknown. We may not be interested in it, but as part of the process we will end up finding it. And we also do not know this Lagrange multiplier function corresponding to the governing differential equation, that is lambda x, and we do not know this uppercase lambda. Okay. Notice that we have put an inequality constraint, as we have discussed in the last lecture and the one before that, and much before when we discussed finite variable optimization. Whenever you have inequality constraint, there are two possibilities. One, it can be active, the other it can be inactive. So, we have to find out whether it is active or inactive by working out the problem, as we will do today. Okay. Noting this problem, the next step is to write the Lagrangian. So, we will move on and write the Lagrangian. So, the Lagrangian for this problem is the objective function 0 to L E A u prime square by 2 dx, plus we have the governing differential equation, which is a function type constraint, which has to be integrated from 0 to L multiplied by that lambda times the governing differential equation itself, which is E A u prime prime plus P dx, and we have lambda times the constraint, which is the functional type constraint, which is A dx minus V star. That is our Lagrangian. Once we have Lagrangian, we have to see what our integrand of the Lagrangian, so that we can write Euler-Lagrange equation by taking variation with respect to the variables that we have. The variables that we have in the Lagrangian are A of x and U of x. A of x is our design variable, U of x is our state variable. We also have lambda x, which is a Lagrange multiplier function that we do not take variation with respect to, because that is not something that we have control over. The problem decides what lambda x should be. Okay. Our necessary conditions are to do with only the function that we do not know. One is design variable, other is state variable. Okay. So, in fact, the governing differential equation is the one that lets us compute the state variable, provided we know A of x. Okay. Now, we take let me write what is the integrand for this problem, that is what is the integral sign. So, that is E A u prime square by 2 plus lambda times E A u prime prime plus P plus lambda times A. That is what we have, and then we have of course what is this integral, right? This whole thing is to be integrated, and then we have lambda times V star, that is just a constant that we do not need to worry about. Okay. This is what we are interested in. Let us expand this term before we proceed, so that we can see u prime, u double prime explicitly. So, let us write this as E A u prime square by 2 plus lambda times, if I expand it, it will become E A u E A prime u, where A and u prime both are functions of x. When you take this derivative, we do normal product rule, E A prime u plus lambda E A u double prime plus lambda p plus capital lambda A. That is our integrand. Now we write the Euler-Lagrange equations, or we just say variation of the Lagrangian with respect to area of cross section being equal to 0. That gives us the Euler-Lagrange equations with respect to A. That is, we write dou f by dou A minus, we have, if you see A prime, there is no A double prime. So, we stop there, dou f by dou A prime equal to 0, okay. And then we will write the boundary conditions later. First, let us write the Lagrange differential equation part, okay. If we do that here, A is here and here and here, okay. Let us write dou f by dou A. The first term gives us E u prime square by 2 plus lambda E u double prime plus uppercase lambda, that is this dou f by dou A minus, then we have to see where A prime is, and A prime is here. That gives us the second equation, second term, which is lambda E u, and actually this is not A prime u prime, okay. Let us see. So, when you wrote dou f by dou A, this should be lambda E A prime u prime and lambda A u double prime. So, this is prime, okay, that the whole prime, alright. So, actually this looks like double prime, let me rewrite that, that is, oops, okay, we go there, A u prime, okay, that is lambda E u prime, and then whole prime, because of what we have over here, that should be equal to 0, right. Let us expand this. Let us write E u prime square by 2 plus lambda E u double prime plus lambda minus. Now, if we take this derivative, okay, we will get two terms, lambda prime E u prime, and we get minus lambda E u double prime, okay, that is equal to 0. Now, we notice that this term and this term get cancelled, leaving E u prime square by 2 plus lambda minus E lambda prime u prime. Basically, that term I am writing in a different order, E lambda prime u prime equal to 0. Let us leave this equation, let us call this 1. In fact, this equation is what we call design equation, okay, design equation, and this is something that may look amusing now, because there is no A here. When we say we are designing a bar, we are actually determining A of x function, but this equation I do not find A, but yet as we will see, this enables us to find area of cross section, optimal area of cross section, okay. That is equation 1, design equation. Then we go ahead and take variation of the Lagrangian with respect to the state variable, okay, because that is also a function. Let us see what f is, which you see at the top of the screen. If we take that, then that will be dou f by dou u, because u is present in integrand f, minus dou f by dou u prime, and then there is u double prime also. So, we have to say we had to include the third term, dou f by dou u double prime equal to 0. We will also have boundary conditions, which we will come to later. For now, let us take this dou f by dou u. Where is u? U is over, actually u is not there, right. If you look at this over there, this is our integrand, there is no u present, there is only, there are terms with u prime, 1, 2 terms with u prime, 1 with u double prime. So, the first part will be just 0, dou f by dou u is not there. Dou f by dou u prime, there are two terms, the first term that will give E A by 2, and then we will have u prime square will give 2 u prime. Okay. So, 2 gets cancelled. So, E A u prime, and then the other one will be lambda E A prime, that is the other term, and this should be prime of that because we have that, and then plus u double prime is lambda E, that is dou f by dou u double prime will be lambda E A, and we have to take double prime because of that, and that should be equal to 0. So, let us expand this. So, first one you will get E A u prime, we have to take another prime of that. Okay. So, I will I will expand it. E A u prime will be E A prime u prime minus E A u double prime. Okay. E A u prime, E A prime u prime, and then E A u double prime when you take it, and the other one here I will leave it as it is. In fact, it is also minus, not plus. The other one I will not expand because I know that it gets cancelled with the thing that comes out of this term that has double prime, where derivative twice. First time we will get this is A prime, by the way. So, we have lambda E A prime plus lambda prime E A, and then we will have prime of that equal to 0. Okay. We will go on further. So, E A prime u prime minus E A u double prime minus lambda E A prime prime, that I did not want to expand because this term here is basically lambda E A prime and prime because we have the prime there, and this one I will leave it as it is, right, that is lambda prime E A prime, I leave it as it is. Okay. Now, if we look at this, these two get cancelled. Okay. So, what we are left with in this case is lambda prime E A, I will write like this, prime minus we have E A prime u prime minus E A u double prime equal to 0. Okay. If our algebra is correct, this is our second equation which we got by taking variation of the Lagrange in respect to u. Let us call this second equation. This is called the adjoint equation. Okay. Yeah. So, this is our adjoint equation, right. So, when we go back to this, okay, let us this is the adjoint equation. We have two equations and our unknowns are a of x and u of x and lambda of x and capital lambda also. So, we have, in addition to this, we have these equation, that is 0 to L a dx minus v star, okay, and corresponding multiplier that should be equal to 0, which is what we called complementarity condition. Whenever we have inequality condition, inequality constraint, we need to have this complementarity condition, okay, and then we have the governing differential equation E A u prime prime plus p equal to 0, which is our governing differential equation. And another thing that we know should hold good is that in addition to this complementary condition, this lambda should be greater than or equal to 0. Lambda can be 0 or positive, but not negative. Okay. So, we have these equations. So, if I call this equation third and this equation 4, we can solve for this problem because we have 4 unknowns, that is a of x, u of x, lambda of x and the capital lambda. We have one differential equation here, equation 1, equation 2, equation 3 and equation 4. We will take a break now, then come back to the solution of this equation in the next part.